Okay, what we were going to look at is fluid pressure. And what that means is if you have some fluid, like the side of a tank, is basically what we're going to, let's say we have a rectangular side of a tank, and we're going to look at how much pressure, depending on whatever the fluid is, water, oil, or whatever fluid they happen to be using, even concrete when it's in liquid form, how much pressure it would put at on this rectangular plate, or it could be a circular plate, triangular, it could be any shape. First of all, let's talk about what pressure is before we talk about fluid pressure. Pressure, and you may know this from physics, it's an R. Pressure is the force per unit of area over the surface of a body. So pressure, and that's why is the force per unit of area over the surface of body. All right, to find pressure, fluid pressure, to find fluid pressure, because that's what we're going to be looking at, what we do is we say fluid pressure, P, is the weight density, so that's weight density, times the height or the depth of the water, or whatever liquid it is. So H is the depth, and we've used W enough, that's the weight density. All right. So before we go on, there's just one little principle that you need to look at. It's called Pascal's principle, and it was in your book. So there's a nice picture in your book. And it's the same Pascal's that made Pascal's triangle, by the way. Um, Pascal's principle, because he was a mathematician and a scientist, he basically said that when you have something, so like here's a nice tank of water, we'll say, and there's something in here. What he figured out that is the force in a liquid is transmitted equally in all directions. And so that's why we're able to use calculus to do this. So the force in a liquid is transmitted equally in all directions. And so that's why we can just use basic integration to do some problems today. So if we know fluid pressure is weight density times the depth of the water, and then we use Pascal's principle that says the force in a liquid is transmitted equally, we can find something called fluid force. And so that's what we've been talking about is force and work. Fluid force is pressure times the surface area. So this is kind of the basis of our integration when we start integrating here in a little bit. Pressure times the surface area, which both of those could be functions that are changing. Usually the surface area is the function that's changing as you move in the depth of the water. All right, so let's say that you have, well, let's just do something easy first. Let's talk about if a plate or something is horizontally submerged in water. If you have something horizontally submerged in water, so I'm going to draw this as my water. So here's some water. Let's say I have a circular plate that's sitting down here and it's horizontal. Well, this is the key. It's horizontal. I actually don't have to use calculus on that because it is horizontal. Let's say that the radius of that circle down there, that circular plate, is 3 feet and the height of the water is 10 feet. We can actually find the fluid force or the fluid pressure. My fluid force would be my pressure times the area. See, because this is laying flat, and I know my picture is not very good, it's all constant. Because although it's a constant, if I put it vertically, that's when there's a problem, but because it's just laying on the bottom, everything's a constant there. So that would be very easy to find. I would take my pressure, which is my weight density times my depth, times the area, the surface area, or the area of that plate. So my weight density of water is 62.4, my depth is 10, And the area of that circle would be pi times 3 squared, which is, you get 62.4 times 10 times 9 pi. And whatever that is, that would be your fluid pressure. And that would probably be this answer, whatever those are multiplied, that would be in pounds because you're talking about feet, so that would go to pounds. So if something's horizontal, it's easy because everything's constant. It's when you have a vertical plate that things get kind of crazy. So let's just say we have a rectangle that's like this. Um, let's say that, let's say this is a 3 by 4 rectangle, 3 feet by 4 feet rectangle. And let's just say that this rectangle is like the gate to, it's a vertical gate to let water in and out of something. We're going to use water again. So what we do here is this problem becomes a little bit more difficult because as you move up on this plate, the pressure is different because the water is not all just 10 feet. H is changing depending on where you are in the plate. And so then we actually have to use calculus. And so we have, how I do these is I like to draw like a representative little disc or rectangle it would be here. Okay, and to get your pressure, you have your force, and this is just like the other ones I did. Your change in force is your weight density times your depth, like we said, times our area. Okay, my weight density is going to stay the same. I'm in water, so I'm going to use 64.2, and that's just your standard one for, and that's in pounds per cubic feet, right? This would be pounds per cubic feet. Now, your depth, and your book labels these very nicely. I actually like what they did. They call the depth the function, they call it the h of y function. So that's your h of y. How far down is this? Well, I drew, and this is where you can get different, you can set it up different, but you should always get the same answer. I drew my axes right here. Okay, and so here's my axes. Here's my x-axis and my y-axis right here. So if I look at this little representative rectangle I drew, this is down from the y-axis. Its depth would just be, depending on where I drew it, is just negative y. Now if I drew it differently, your depth might be different than mine, but we should still get the same answer. I'm going to, by the way, let's just say that this is down 1 foot. So let's say that the top of this plate is 1 foot below the water. Okay, so the area of this, so you want the area, and this one I like because it's a rectangle, so it's easy, it doesn't change. No matter where I draw this little representative rectangle, if I drew it here, or if I drew it down here, or if I drew it here, the area of that stays the same. It would be 3 times 4, and if I'm talking about surface area, you would also have to include its height, which would be delta y. So I'm going to integrate. Now I have my function. I have 62.4 times negative y times 12 times dy. Now the only problem that I have to figure out here is I need to integrate from where to where. Well, that's why I needed to tell you this was 1 foot below. You need to integrate from the depth of your metal or your plate that you have in the water, the surface that you have in the water. So if this is at 1 below the water, that'd be negative 1, and if it's 3 feet wide, that'd be negative 4. So you're going from negative 4 to negative 1. And then you would integrate that. Okay, so when you integrate that, you get like 2,808 pounds of pressure. And make sure when you integrate that, I mean, these are constants. So you end up with like whatever that is, 62.4 times 12. I don't know what that is. From negative 4 to negative 1 of negative y dy. That becomes negative y squared over 2 from negative 1 to negative 4. And because they are negatives, when you put in negative 1 first and you subtract the value of negative 4, you do get a positive number. So just be careful with your negatives there. Okay, so one other problem I want to look at, see that one I put below the x-axis. Let's say that let's try one above the x-axis just to see how it differs. Let's say you have a triangle that looks like this. And let's say that its distance is 4 across and I can't even deal with that triangle. Hold on. Let's do like a real triangle here. Um, so let's say I have a triangle that looks like that. Okay. And so then let's say that it's 4 across by 3. So it's a 4 base by 3. And we'll use feet again. And we'll just use water again to make it simple. Let's say this time I want to draw my axes different. I'm going to draw my axes here and here. So I would still have a rectangle representing in here. I'm going to just say like this is the side of a tank again, tank full of water. So my fluid force is going to be my pressure times my area. And the change in that force, because it's going to be different, this one's a little bit harder. My pressure is going to be my weight density times my height times my surface area. And your book uses L of y for surface area, or your area of this rectangle is what they're talking about. And then obviously times your change in y. And your change in y becomes dy in your function. All right, so this is, I want to just show you this. I probably won't integrate it, but we have our weight density, which is 62.4. I drew this above the x-axis, so this time I'm going from 0 to 3 because I said this was 4 by 3, so this would be, this ordered pair here would actually be 2, 3. All right, the height of my, no matter where I draw my rectangle, so if I pick this point right here, the height would go from 3 down to here, so that would be 3 minus y. Okay, now the length of my rectangle is going to be this L, which they represent as length, but it's actually that area, right? I have to figure out this length. Well, no matter where I put it, it's x, right? The distance from here to here, no matter where I put this rectangle, is x. So I have 2x times the height of that rectangle. That's why we get the delta y. So the area of that rectangle is this length times this height, which is dy or delta y. Okay, so the only problem I see here is that I have two variables. So that's a problem. What you need to do is to change this so it's in all terms of x. And so what you can say here is that this side of this is a line. And so that line would actually equal y equals 3 halves x plus 0. That's the equation of that line. So I can say, well then x would equal 2/3 y. So instead of putting in x, I'm going to put in 2/3 y. Now for this one, you could just use a line. If it's a circle, you're going to have to use the equation of a circle. If it's a trapezoid, you'll have to use the equation of a line. So then you would integrate all of that. And I think this answer comes out to like, I don't know, 332.8 or something like that pounds. But I just wanted to make sure I showed you one where we changed it. Okay, that's it.